This is the third problem we're going to solve today. This is, you can see the schematic here. We actually need to calculate the pressure drop, head loss, and the pumping power. For this problem, actually this is 60 meter long section, and the water is flowing this way. You can see this is the inlet, this is the outlet of the pipe. The water temperature is 15 degrees centigrade. The density, the viscosity, everything is given. It is 5 centimeter diameter and horizontal pipe. The other thing is it is made by stainless steel. So the flow rate is given here. You can see the rate. We need to calculate the pressure drop, the head loss, and the required pumping power. I actually know this, how to solve this sort of problems, but previously we solved the problem. It was for laminar flow, and this question is for turbulent flow. So now the method to calculate the friction factor, it should be different. So to make this problem short, what I will do, I will not write the assumptions, but I will tell you. So the assumptions are, I will not write it down. So the assumptions, the first is it is steady and incompressible flow. We'll say this is fully developed flow. That means the entrance effects are negligible, and for this pipe, we'll say it has no bends, valves, or the connectors. So that means it is only like this horizontal pipe. So that's the same diameter, and no pump or the turbine we're using in this case. So that's the assumptions. And now the properties are given. The density is 999. This is kg meter cube, and the viscosity is 1.138 10 to the power minus 3 kg per meter second. So that's the properties we know, it's given. So the first thing we need to calculate is from the problem is, it says the pressure drop. So the pressure drop delta P, we know this is equal, the pressure loss or friction length diameter over rho v square and 2. So that we know the formula. So that means, as usual, we know F, we need to decide whether the flow is laminar or turbulent. So I did it, and we got it is a turbulent flow problems. So what do we know? So we need to calculate the Modi diagram. So if we use the Modi diagram, then sometimes we may get some approximate value, not appropriate value. There should be some errors. So we can avoid this, and we can use this formula. You see, this is epsilon over d, 3.7 plus 2.51. This Reynolds number is square root of f. So this is the formula that we can use. This is Colebrook equations. So actually Modi diagram is obtained from these equations. Okay, so we can use this, and we can get the f from here. So to get this, we need epsilon over d, and we need the Reynolds number to check whether it is laminar or turbulent. And in this problem, the volume flow rate is given, so we need to calculate the velocity. Okay, so that's the overall, actually, the procedure. Initially we will calculate the velocity, Reynolds number, then this, then we'll get the pressure drop. Okay, so the velocity v, it is the volume flow rate over the cross-sectional area. So it is given, if you see in this question, 6 liter per second, converted into meter cube per second. So 0.006 meter cube. We can, and we know the area is pi d square over 4, pi d square over 4. Okay, so this is 0.006 meter cube per second. Pi diameter is 5 centimeter. Okay, so 0.05 meter, this is a square over 4. So we'll get it is 3.06 meter per second. So that's the velocity. So we have got the velocity. Okay, now we'll calculate the Reynolds number. So the Reynolds number, you'll see the formula is rho p d over mu. Rho is 999 kg per meter cube, so I'm not writing the units. This is 3.06 meter per second, and 0.05. This is the the diameter, and the viscosity, it is 1.138 10 to the power minus 3. So Reynolds number is 134,300. So you see it is clearly greater than 2300. So we can say the flow, it is turbulent. So we cannot use the previous formula that what we did for friction factors. So that means now we need to use this formula, that means this Coulomb equations. If we want to use the Coulomb equations, we need to know the epsilon, the roughness. It's not given in this problem. So now we need to use this table here. You look this table 8.2 from the book. So it will tell you the roughness of the commercial pipes. In this problem we have stainless steel. So for stainless steel it is 0.002 millimeter. Okay, 0.002 millimeter. So we can say epsilon over d, it will be like 0.002 millimeter, and the diameter was in the question is 5 centimeters. So then you can say it is 50 millimeter. So then this epsilon over d, it will be 0.0000. Okay, so 000, it should be one more 0 and 40. So that's epsilon over d. So that's, we got the values. Now we need to substitute this value to the Coulomb equations, which is 1. The Coulomb equations are 1 over the square root of f, it is equal negative 2.0 log epsilon over d over 3.7 plus 2.5 on over the Reynolds number and the f. So if we solve this, we actually need to use the calculator. Okay, so if we solve this, then we'll get f, it is equal 0.0172. So you actually need to use the calculator. So here when we need to use the Moody diagram, we can actually use these equations, and that will save a lot of our time. We just need to use the calculator, and that will give us actually the more appropriate solutions. So now we got this value f, and now we are looking for the pressure, the delta P, which is the F L over D and rho B square over 2. So the F is 0.0172. we got length 60 meter, diameter is 0.05 meter, density 999, velocity 3.06. this is square over 2. So we'll get the pressure is 96,540 Newton per meter square. So we just converted into like this, it is 1 kg meter per second square. So this is the conversion unit we used here. Okay, so it is Newton meter square, or you can say it is 96.5 kPa. Okay, so that's the the pressure drop. Now the head loss, the head loss, we need to calculate the head loss. For head loss, we know the formula. We solved it for previous problem. So head loss Hayes L, this is equal F L over D B square and 2G. So F again 0.0172, L is 60, D is 0.05, and the V square is 3.06. this is a square over 2 and 9.8. So the Hayes L will get it is 9.85 meter. 9.85 meter. So this is the head loss. Okay, previously we calculated the delta P, the pressure drop, and then head loss. Now the pumping power. So if we actually want to calculate the pumping power, this is very easy. Volume flow rate and the delta P. So the volume flow rate is 0.006 and the delta P is 96,540. If I didn't write the units here, so if a unit convert it into watts, so it should be like this, and we'll get it is 579 watt. So that means we need this amount of power to overcome the friction loss in the pipe. So that's the problem, and yeah, that's it.